I ran into a girl last night that I taught my very first year I ever taught. And my very first year I ever taught, I taught like 12th grader Algebra 2. Nothing but 12th grade. We don't even have that class anymore because we don't track anymore. But needless to say, they hated math. But they were really fun. But I mean, they hated math. And I taught like all the week classes, but they gave me the job of being the math team coach. So I would bring them to my math tournaments. It didn't go well. It took a couple of years to convince them that I probably needed to teach some really bright kids if they wanted to have a math team. Anyway, lots of interesting stories. But she was telling me how, the only way I function is on Vyvanse, and she's, I guess, 40, what now, 40, I would have been 25, 18, 7, 46? She's like, that's all I can do. You think I'd get on it, all my kids are on it. Anyway, so today we're looking at vectors and complex numbers, specifically complex numbers, so that we can, and I'm paralleling them, I'm comparing them to something that most of you knew really well, at least the basics of the vectors. Most of you know that really well, and you can see that there's a lot of similarities. Like a vector in unit vector form has an I and a j, and the I has nothing to do with imaginary, does it? Just has to do with directional movement. Well, on an imaginary number, you've got a real and an imaginary part, and the I actually means that it came from a radical that was negative, right? But it also means when you move, unlike a vector where you're going to move 2 to the right and then maybe 3 down and you're going to draw an arrow, a similar complex number, which again has nothing to do with this, I'm just showing you the relationship. I'm going to move 2 to the right and 3 down, just like I would have here, only the only difference is it's a point. All right, we talked about this last year for a little bit. I know because we just covered it last year. I'm sorry, we just covered it in Algebra 2 a week ago. But building off that, if you look at magnitude, if you remember the magnitude of a vector was the length of it. And since I'd gone over 2 and down 3, I used Pythagorean theorem to find that. And I completely ignored the I and the j, right? Because the I and the j just showed me which direction I was moving. Well, absolute value of a complex number, which we learned last year, but again, we spent this much time on it. Absolute value is the same definition. Because in absolute value, we said, you learned with Miss Tyree, I think, that absolute value was the distance that that number was from 0 on the number line. But when it turns into a plane, it's still distance, right? So it's the distance from the 0 on the number line, but it's kind of like the origin now on a plane, but it's the real imaginary plane. So again, you're going to ignore the i's, just like you ignored the i's and j's, and you guys did a really good job of that. I think there was one person, and it wasn't somebody in this class, that accidentally put the I in there. Everybody else remembered to just take the 2 numbers and plug them in there. So absolute value, complex number, just like magnitude of a vector. Okay, and then when you start talking about direction angle, there's also a direction angle of a complex number. So the direction angle, again, is measured from 0, and you'll see exact same definition. Here it was inverse tangent of y over x. Here it's inverse tangent of y over x. Here I didn't add 180 because the x was positive, and when I go over 2 and down 3, I'm in the 4th quadrant. And does inverse tangent lie? Sometimes, but where does it lie? 2nd and 3rd, right? It can't give you those values, so you have to add 180. But this one you can see is going over 2 down. That's in the 4th, you're okay. Right? Well, same thing here. I don't have to add 180 here. I'm fine to use a negative. But I don't have to add 180 right here because it is in the 1st or the 4th. So as long as you're in the 1st or the 4th, you're okay with direction angles of complex numbers, just like you are with vectors. Trig form of a complex number. Now, trig form of a vector, we learned, we didn't use it a ton, but we have the magnitude on the outside and then cosine theta I plus sine theta j. Remember this? That's trig form of a vector. Well, there's not much difference. If I give you a complex number, you're going to find not the magnitude, but the absolute value. But you're still going to find the direction angle. So what's the only difference other than maybe a couple bars right here? This one says ij, but this one has what? Nothing, and we put the I out front, and I'm probably for no particular reason other than it's imaginary now, and we try to put imaginary where it's easily distinguishable from the rest of it, and we don't want to confuse it with that I. Honestly, they probably ought to have the I and the J out front on these, but they don't. So again, real part, imaginary part, and then if I simplify that, you can see that I can take that magnitude and I could multiply it in there just like I could multiply it in there to put it back in a different form. But the trig form, you look at it, it's really the same idea. So if I were to give you magnitude and direction, know that you can go and plug it into trig form of a vector. You can do the exact same thing with a complex number. Are you all with me so far? Okay, now multiplying and dividing. I'm not going to spend a lot of time on this because I want to get to the Mobley's theorem as quickly as possible, but we know how to FOIL, right? Take your time. On this test that I just gave my Algebra 2 kids, some of the more missed stuff they had was FOILing stuff out. They would do stuff like 3i times negative 4i is negative 12i. And then, of course, they're going to add that negative 12i to these other i's, and the problem's going downhill quickly. So remember, if there's two i's, there's an I squared. Also remember that sometimes I give you stuff unsimplified. What if I were to give you, I don't know, how about, if I were to give you that, what would you do first so that you could see the problem more clearly? You take your eyes out, right? Because if I don't do that, if I go and multiply this times this, right here, and that's the L in FOIL, I'm going to get negative square root of 144, which is going to give me negative 12. But the reality of it is, if I take my eyes out first, by pulling that I out and pulling that I out, then when I multiply, I still get root 144, but I get this negative I squared. And what does a negative I squared do? It becomes a positive 12, not a negative 12. So if you don't take your eyes out first so that you can see more clearly, the problem's going downhill. And that class did it a ton, and it really hurt a lot of them, because this is, the hope is that these problems are the easier ones of the bunch, and that you really get that foiling stuff down or whatever. And then when you get to stuff like this, this is division technically, but you could call it simplifying, because we don't like to have what kind of denominators? Imaginary or irrational. So we like to say we want to rationalize our denominator, and we do that by multiplying by a conjugate on the top and the bottom. And I have a lot of people in this past test in Algebra 2, and they're a pretty smart group, but they multiplied that and they go, oh yeah, it goes away when you multiply by the conjugate. It doesn't go away. I mean, it's possible that it goes away, but this one certainly didn't go away, right? You got 25. What goes away when you multiply by a conjugate? The middle terms, the oi of the FOIL. That part goes away, but you're still left with the first times the first and the last times the last, which ends up giving me a value. And then also, do we ever leave like this? No, because that's a form issue. That's like chewing with your mouth open. We want to always put it in A, put the real part over the real, and the imaginary part over that real, and make it A plus B, and then you can leave the I on the top or off the side. All right? So anyway, that's the stuff that I think you probably kind of know, because of the relationship between that and vectors. And then this last part right here, I think you kind of know already. So this comes to the new stuff. So the new stuff, and I really want to show you the proof of this, but I'm not going to have time today. Maybe I can show you tomorrow. But if I have these two imaginary numbers, okay? And by the way, I don't know if you remember this, but you might remember last year, I said that sometimes people get kind of excited about naming imaginary numbers Z. Like sometimes they'll go, all right, here's this imaginary number, 2 plus 5i, and I'm going to call it Z1. And then there's this other imaginary number, you know, right here, and I'm going to call that Z2. So what's Z1 times Z2? Now, I don't know what the fascination with labeling stuff like that is. I don't know why they just don't write that times that. But regardless, people will do this in mathematics textbooks. So if that happens, if they label stuff Z1 and Z2, and they say find Z1, Z2, don't freak out about that. Just do what you're told. Now, if I really did take this vector, this complex number and this complex number and multiply them together, there is a rule to do that, and it's a shortcut. Because honestly, if you actually did have to take these and multiply, like if I actually took this right here and multiplied it by this right here, I could definitely, the numbers on the outside, put them together. But what would I have to do with all these, this A plus BI thing? I'd have to FOIL it out. And after I FOILed it out, you would see some of your trig identities showing up. In fact, what you would end up seeing is a cosine of an alpha plus beta identity, and you'd see a sine of an alpha plus beta identity. And you'd do some grouping and simplifying, and you would simplify it to this. And there's a proof I could show you that shows you that. It's just you foiling it and then noticing little patterns. But you don't have to do that. All you have to know is to multiply any two imaginary numbers that are in trig form. All I end up doing is doing what? Multiplying their absolute values and adding the angles. So it's a shortcut. So I'm not going to want to multiply this way if I already have it in A plus BI form. If it's in A plus BI form, FOIL it. But if it's in trig form like this, a great way of multiplying is to accept this rule and go, wait a minute, if the rule works, multiply these, add the angles, and by the way, these angles always match and these angles always match. So once you add these two right here, you can just put it there and there. Don't forget the I, and that's your trig form. And then if you really wanted to write it in A plus BI form, all you'd have to do is add these together to get one angle, multiply these together because they're just two numbers. I mean, that magnitude, I mean, absolute value might be 8. This one might be 4. So you multiply them together, and then I could just distribute it in, and I'd have something in A plus BI form. But it's so much easier that way than changing them into A plus BI form first and then doing this. Because more than likely, if you change these to A plus BI form right now, with angles in there, you're probably going to get some really ugly decimals. And then you're going to be multiplying really ugly decimal values together. Are y'all seeing this? So that's how you multiply. And then if you go and look, the same thing is true if I jump down here with dividing. And I'm skipping this stuff right here, but anyway, I'm showing you.
What is CIS?
What is what?
Like CIS.
Oh, you're going to find with Demagog's theorem, especially when we start doing roots of these numbers, you're going to be writing so many versions of the number, you're going to get sick and tired of writing cosine 20 plus I sine 20, cosine 80 plus I sine 80, cosine 140 plus I sine 140. You're going to be writing all this and you're going to go, you know what, a shortcut for cosine blah plus I sine blah is just CIS of the angle. So a shortcut that you can use, so if this had been like cosine 20 degrees plus I sine 20 degrees, then I could make the shortcut, I could write CIS, this is CIS 20 degrees, and then all mathematical people will know what you're doing. So if you want to apply that, great, it's just a shortcut. And also, I don't know if you remember this, but in, no you don't, because we didn't do summer reading. In summer reading, there was this formula. It's called Euler's theorem. There was this formula here that is true. E to the I theta power equal, you don't have to write this down, it's not going to be tested. But I was showing you a little proof right here that this right here, this imaginary number, like Z1 right here, could be rewritten as Z1 times E to the I theta. Okay? And if this thing was written as Z2 E to the I theta 2, then to multiply Z1 by Z2, I would go Z1 E to the I theta 1 times Z2 E to the I theta 2. Now, what do you get when you multiply these together? Well, certainly I can put these together. And what do you do to multiply like bases? Keep the base and add the exponents. So now I'm going to take E to the I theta plus I theta 2. And think about it. If I have E to the I theta 1 plus I theta 2, if the angle is theta, I could take theta 1 plus theta 2 and plug it in there as well. And that's another proof to show you why this is like it is. But you don't have to know the proofs, and that's a different proof by foiling that would make more sense to you than using this, but this made really good sense if we did summer reading. But I keep forgetting that we did not do that this year. So anyway, that was a proof for multiplying. So here's an example. If that was your Z1 and that was your Z2, how do you multiply the two? Really easy. Take the 3 and the 6, multiply them together, take the two angles, add them together here and here, clean it up. And 18 cosine 65 plus I sine 65 would be your answer. And if you like the shortcut, 18 CIS 65. All right, and then division works almost exactly the same way. And again, you can ignore that proof there, but check out the division. If this is Z1 and this is Z2, what does it look like I'm doing to divide? Instead of multiplying those, I divide them. Instead of adding the angles, I subtract them. So very similar formula here. And again, this is just a one proof using Euler's theorem. There's another proof you could make by rationalizing, by multiplying by a conjugate, which is a mess, but it does work. But anyway, that's the proof of this. As long as you know how to use it, like right here, there's Z1, there's Z2. What's Z1 over Z2? 3 over the 6, 20 minus the 45. You get this. I like you to clean up the angles and let the angle end up between 0 and 360. That's a good form issue. It's not overly that big of a deal, but I like for you to do that. So when you add 360, you get to here. That's not because it's in some quadrant. It's just because I'm trying to let you have good form. And then you just leave the 1/2 out front. And if you want, CIS works a little bit easier. It's a little less writing. And again, CIS is cosine, I sine. So it's just a notation that explains this without writing so much. Not too bad? Okay, I got 4 minutes. I'm going to be able to introduce de Moivre's theorem, but not be able to do a whole lot with it, but we're going to pick it back up tomorrow. So de Moivre's theorem is a way of taking what we just learned, which is how to multiply a complex number by another one, and talk about how to raise it to a power. Now, I want to go back to this. What if I went to this multiplication problem and I said, hey, it's Z1 times Z1, and the angles are the same? That's not multiplying, that's dividing. What if I said, all right, on this multiplying right here, instead of having a Z1 and a Z2, what if they were both Z1s? What would happen right here if I went Z1 times Z1? What do I end up with? Z1 squared. So technically, Z1 times Z1 means Z1 squared, and that would equal Z1 squared. And then what do you do with the angles? What's theta 1 plus theta 1? It's 2 theta 1. Are you seeing that? Now, what do you think happens if I go Z1 times Z1 times Z1? So Z1 cubed, if I had that, and then what would it be if I had theta 1 plus theta 1 plus theta 1? 3 theta 1. So you just invented a rule. You could have put your name on it. Beaten de Moivre to the punch if you were like 1,000 years older. Anyway, that's de Moivre's theorem. He just says to raise something to a power, you can build off this principle, and all you have to do is raise the magnitude to that power. Check it out. I got an imaginary number. To raise this imaginary number to a power, raise the magnitude of the power, multiply the angle by n, and then clean it up. Now, if I was raising something to the 10th power, you're going to get stuff like 2 to the 10th, 3 to the 10th, maybe 5.723 to the 10th. If it's an ugly decimal, pull out your calculator. What's going to most likely happen to your angle? What's 110 to the 10th? Huge, right? So you're more than likely going to get a really big answer for that. So when you get a really big answer for that, and by the way, this is the proof right here. Like on this one, it was 80. No big deal. Leave it. But if you end up with a big number, like when you go 4 times 275 and you end up getting 1100, make that final angle between 0 and 360. All right? But that's de Moivre's theorem. So remember, de Moivre's theorem is how we multiply stuff that's in trig form. So what do we do when it's not in trig form? And how do we put something in trig form? We find its magnitude. Check it out. Find the magnitude and then find what? The direction angle. And take the magnitude and the direction angle. And now that it's in trig form, I can raise the z to the 6. So check it out. Trig form, raised to the 6 using de Moivre's theorem. We're going to talk more about this tomorrow. I know we ran a little short on time. No worries. We'll get you straight.